All right, yeah. So our next presenter is going to be Hsia Yeo, doing a talk on triboelectric charging of lunar dust by rover wheels. So Hsia, go ahead and take over whenever you're ready.
Yeah, is my screen visible?
Yep, I can see it, and we can hear you.
Great. Okay, so my name is Lisa, and I work at the University of Colorado with Mihai and Shu. And this work that I'm about to present was done in collaboration with Edita from UCF and George Grost and Joseph Minafra from the Ames Research Center. So, as everyone by now in the session should know, the surface of the moon is covered with a layer of fine dust called the regolith. And this dust, as Deborah mentioned, I think 2 talks ago, it's a key challenge for landed missions and long-term human habitats. It's a human health hazard, especially when it is inhaled, and it can clog mechanical joints, obscure sensors, solar panels. It can cling to equipment, and if it does so, it poses the risk of electrostatic discharge. So I've included here a picture of the Apollo 17 astronaut, Harrison Schmitt, and you can see his spacesuit is almost entirely coated in lunar dust during his field investigations. I also want to give a bit of quick context about the lunar plasma environment before I delve into the specifics of dust charging. I think yesterday Bill Farrell gave quite a good talk related to this topic, so I'll be brief. We know that UV radiation and solar wind help make up the lunar plasma environment, which then go on to charge the dust grains on the lunar surface. And on the day side, for instance, photoelectrons dominate any dust charging processes that take place, but on the night side, the surface potential can be up to tens or even hundreds of volts because the solar wind electrons fill in the wake ahead of the solar wind ions. And then on top of that, we have local topographies like craters that alter the solar wind flow. So all these natural processes go on to affect the charging of the dust on the moon. But what I would like to focus on is triboelectric charging. And this occurs when 2 materials rub against each other, and what happens is they're going to transfer charge between them. So if you've ever removed a sweater and you felt that static electricity build up, or you rub your hair against a balloon, you've had firsthand experience with triboelectricity. So the amount of charge that's transferred depends on the type of materials being rubbed together, how vigorous or long that rubbing is, as well as the specific surface properties of the materials in question. And previous work by Gross, Sharma, Sekafu, Stanovsky, they focused on triboelectric charging of dust with various materials as they interacted with plates and beads and so on. But this work in particular focuses on the interaction between rover wheels and dust. So I've included here a couple of screen grabs of the Apollo 16 mission, and we can see that dust is kicked up in copious amounts by the rover, which then begs the question, well, how much charge is being exchanged between the dust and the rover? And as we return to the moon, knowing the answer to how the dust and wheels interact with each other electrically is going to become more and more important. So in 2005, Jackson et al., they modeled the charge on wheels as they interacted with dust. But in the next couple of slides, I'm going to present some experimental work on the triboelectric charging of the dust itself. Okay, here is our experimental setup. It's simple and direct, and it was designed in collaboration with the NASA Ames Research Center. And it just measures the amount of dust charge on wheels. The amount of charge on dust that has been kicked out by a rover wheel. And it's the first of its kind, and it's very straightforward. We have a rover wheel, it's spinning on a bit of dust, and it's kicking up this dust that's then collected into a charge detector. It's also known as a Faraday cup. And here's a picture of our little rover that we used at the dust bed. So after this initial proof of concept work was done at the Ames dust bed facility, I went back to Colorado and I constructed a similar setup, this time with just a single wheel that spins on an axis. And it allows me to change the wheel speeds as well as the material on the wheel and the type of dust being investigated. So these three variables are going to be explored in the slides to come. So before we go into that, let's see if this works. Just our rover wheel in action, kicking up dust into our detector. And the graphs on the right represent the charge signal events. So the initial rising peak, let's see, well, it's better. The initial rising peak is proportional to the amount of charge that's on the dust. And then this can easily be calibrated by inputting known charges into our Faraday cup, which we did. And the rest of the curve, as it falls and rises again, is characteristics of the internal circuitry of our system. There we go. So without further ado, here are some results. The graph on the right shows the charge distributions that were measured out of different dust simulants as they interacted with a rubber wheel. So on the x-axis, it's the dust charge in picocoulombs, and the y shows the relative frequency with which we measure these charges. So we can see right off the bat that the dust charge that we measured is overwhelmingly positive, which is good news in a way, because it shows that what we are measuring is interaction between a rubber wheel and the dust. So if what we were going to see is dust-dust interactions, then I think I would expect an equal distribution of positive and negative charges. But because rubber is extremely electronegative, it loves to collect electrons, and this leaves the dust particles that it interacts with positively charged. And that's exactly what we're seeing. Another obvious difference that we are noticing here is that when we use different dust simulants, the charge distributions are pretty different. So in the first row, GSE1A, that's a commonly known lunar simulant, and it's a Martian dust simulant, and the final row is the asteroid simulant. Yeah, and finally, I also want to point out that in some cases, the maximum charges that we are measuring on these dust grains can be up to, hundreds of volts. So another variable that I found that changes the dust distribution, charge distribution, is the wheel speed. So here is some data that shows two different dust simulants, each interacting with the same rubber wheel, but at different speeds. So each of these graphs represents somewhere between 2 and 400 data points. And intuitively, you might expect that a higher wheel speed would lead to a more positive charge distribution. But at least in this case, for this set of rubber wheels, we instead measure a slight negative shift in charges at higher wheel speeds. And the reason why this might be, I suspect, is that as I was taking this data, I noticed that there was an increased amount of dust sticking to the wheels at higher wheel speeds, which leads me to suspect that more dust-dust interaction is taking place. If you recall, I think in the previous slide, I mentioned that if the triboelectric charging interaction was purely between dust and dust, then I would get an even distribution around zero charge. So this amount of dust that's being stuck to the wheel is something that can be quantified, and it's on the top of my list of tasks once I manage to get back into the lab and actually get more data. And a final observation that I like to share with you is the difference in charging when the wheel material is varied. So here we compare rubber and PVC wheels with the same dust simulant, and notice how for the rubber wheels, there's a much larger variation in charge. Larger variation in charge that we're measuring. So how can we use this knowledge to plan future rover-based missions? We know now that the charging effect is significant and that it depends on the type of dust that the rover is traveling on, but also what wheels it has and how fast it's going. On top of that, there are a few other factors that we should be careful about. For instance, in the absence of sunlight, we expect the dust to stay charged longer because there's no plasma to help dissipate that charge. But Well, and so this means that if we were to set up a lunar base in a permanently shadowed region, then this effect is something we're going to have to be extra cautious about. And this bit of research also lets us start to maybe think about recommending a range of safe speeds for rovers, depending on where they are and what the tolerance of the equipment around it is. And also note that as the wheels are charging dust, the wheels themselves are also simultaneously being charged back in the opposite polarity by the dust. So this effect can be used to measure the triboelectric charging of the dust in situ by including electrometers, for instance, attached to the wheels. And finally, I'd like to just share once more some of the next steps I'm excited to take, measuring dust adhesion versus the wheel speed. And something that I also want to look into is whether dust is clumping as it enters the dust detector. There are a couple of papers out there that predict that this will happen for certain kinds of dust, so I'd like to look into that. And maybe one day we can start to build a repository of information depending on dust type and wheel materials so that we can be better prepared for any sort of mission planning. And that is it for me. Thank you.
I want to thank you so much. That is very, we have a time for a few minutes, for questions for a few minutes. We have one submitted by Alex Hobbs. He said, you said that max charges on dust grains are equivalent to hundreds of volts. How are you defining a grain with respect to size mass?
That was done as an estimate. So we have a distribution of dust sizes and we know the density of that. So yeah, so we know the dust size, and therefore as an estimate, we just took the voltage, we assume it was a sphere and calculated. Yeah.
Okay. So Micah, I'm not going to even try the last name because I don't want to mispronounce it. He asks, is there any time dependence of the dust charge signal, or is every touch of the wheel statistically similar?
That is a great question, and something we are also hoping to look into. So these experiments were done at atmospheric pressure, but we know that there is moisture in the air, for instance. So the charges are going to change over time. And something we're hoping to be able to do is repeat this in a vacuum chamber so that we are more sure of the charges on the dust. So yes, that's a really great point.